Kia ora team, 2020 Level 2 Mechanics, let's tackle this question. Alex and Joe have decided to take a road trip. They start from rest on a straight road and accelerate at 4.2 meters per second. While waiting at the traffic lights, Joe has to put on the handbrake to stop the car from rolling down the steep 10-degree slope they are on. The mass of the car and the occupants is 1,600 kgs. The diagram shows the friction force acting between the tires and the road, and that's what stops this car from rolling down the slope. I add labelled arrows to show the other two forces acting on the stationary car. Okay, that's simple enough, let's do it. So we've got our friction force that's already shown here, okay? And the other force which is acting on the car, pretty obvious, is gravity. This is the thing that's pulling it down and stopping it from floating anywhere else. So FG, remember we have to label our diagram just like the question has asked. And then we've got another force which is acting on the car. And this is the lift force, all right? So let me add that lift force, and it's an upwards force. And remember, it has to be perpendicular 90 degrees to the surface that this object is on. So this is why I've drawn it this way. Let's not forget to label FL for lift force. Cool. So we've done I, okay? So let's tick that question over there. And I believe that's worth and achieved, according to the marking schedule. All right, next question. Complete a labeled vector diagram showing how all three forces, add together. All right, remember whenever we're adding vectors, we have to add the vectors head to tail. Let me show you what I mean by that. So we've got our FL, which is going up in that angle. I'm literally just displacing these vectors, keeping the angle the same. So that's FL. And then what I have is I've got FG, gravity, and so I'm going to add its head. I have to make sure that the head is added to the tail of my previous vector, okay? So that's FG. And then finally, I've got FF, which is a friction force, and it's on that 10-degree slope, okay? And so I've just added its head to the previous tail, which is FG, and this is my friction force. Okay, cool. We've done a labeled vector diagram showing how all three forces act together. Something I also would like to add is that 10-degree angle, okay, which is shown in our diagram. But where the heck do we add this in our vector diagram? Let me show you a little trick. So to figure out where that 10-degree angle goes, the reason why I like to add this angle in is because later on you'll see that we have to use a bit of trigonometry to figure out one of the sides of this vector diagram, and we need an angle for trig. So may as well add that now to save us the trouble later. What I want to do, first step, is to simplify that diagram that we've done. So I like to simplify like this. So I've got a little car as my dot, and then I know that we've got a friction force going at 10 degrees to the flat surface. I've got my lift force, which is perpendicular to that. Let me just move that across. Perpendicular to that friction force. I'm just labeling them. Then I've got my lift force, and then I've got my force of gravity acting down, straight down. It's got to be straight. Okay, and so now here's the trick. Once I've simplified the diagram like this, now what I have to do is displace the gravity vector so it's in between my lift force and my friction force. How do I do that? Let me show you. So I'm literally just taking my gravity force and redrawing it so it's in between my two force vectors that I've already got, FL and FF, okay? So what do we do from here? How is this going to allow us to figure out where this 10-degree angle goes in our vector diagram? Well, let's have a look. I'm going to get a different colored highlighter just to make everything clear. Here's what I want to show you. So between our flat surface, that highlighter is way too thick. Let me just make it slightly smaller. Okay, so between our flat surface and our displaced gravity force, can you see how that's formed a 90-degree angle? Okay, in the pink, those two lines have formed a 90-degree angle. As you can see, 10 degrees, okay, of that 10 degrees of that 90-degree angle is made up by the slope. So what is the remaining angle going to be within that 90 degrees? Okay, so 10 degrees is made up by the slope. How much of an angle is remaining? Well, simple math, okay? Simple math, it's going to be 80 degrees. Okay, 80 degrees makes up the rest of that 90-degree angle between our force of gravity and the flat surface. Okay, so we want to figure out the angle that is in between FG and FL. Okay, how do we figure that out? Well, as you can see, let me get a different color. Between I might get a highlighter instead. Between FL and FF, between our lift force and our friction force is another 90-degree angle, okay? Between our lift force and our friction force is another 90-degree angle, okay? And so we can see that out of this 90-degree angle, we've got 80 degrees made up by our force of gravity and our friction force. So 80 degrees of it is made up here, okay? So what is this remaining angle going to be? Okay, so 80 out of the 90 degrees is made up between FG and FF. What is left over? Well, it's going to be 10 degrees. Okay, so as we can see from this method, we know that the 10-degree angle is occurring between our lift force and our gravity force. So if we look back at our diagram over here, we can add that 10 degrees between our lift force and our gravity force vector, which is right over here. Another angle I like to add is our 90-degree angle. So we can see from this diagram that one of the 90 degrees that's occurring between two vectors is between our FL and FF vector, okay? Between our FL and our FF friction vector. So on our diagram here, we know that there's a 90-degree angle occurring between FF and our FL vector. Okay, so we've got two angles that we've added to our diagram, which will be helpful for trigonometry later on. Okay, so now that we've done the hard yards, okay, we've done that to a good level, the next thing that we have to do is work out what C is. So by first working out the force of gravity on the car, show that the value of friction force required to keep the car stationary is 2,700 newtons. Okay, so it gives us a clue on what to do. It tells us first to work out the force of gravity on the car. Okay, so that is going to be using this equation here. I'm going to do Fg for gravity. Fg equals m times a. That's the equation that we should use, and that's on your resource sheet. Let me highlight that. So let's do what the question is asking us to do and work out the force of gravity on the car. So let's substitute what we have. In the question it says that the mass of the car and the occupants is 1600 kgs. So we could plug that into our mass value over here. Acceleration due to gravity is always going to be 9.8 meters per second. And if I plug that into my calculator, what we should get is 15680 newtons, okay? And that is the force of gravity. So we need to use that to find the value of the friction force required to keep the car stationary, and it should be around 2,700. So let's go back to our force diagram over here, okay, and see how we can use this to help us work out our friction force. I might highlight that with a pretty color. So this is what we want to find out. So far, we've worked this out from over here, okay? So let me just redraw it so it's clearer. So we've got FL, we've got our gravity, and then we've got our friction force. Okay, and so we just worked out that the force of gravity on the car is 15680. Let me add that angle in there. Is 15680 newtons. We want to figure out what this is. Okay, so using trig, let's see if we can do this. First step is to add and label our vector diagram according to the trig rules. So we've got the adjacent, which is in between two angles. We've got the opposite, which is opposite the angle of concern. And then we're left over with the hypotenuse on this side over here. So let's use our known hypotenuse and our opposite, which is what we want to try to figure out. So whenever we are dealing with O and H, we have to use our SO, aka our sine function. So let's write out that equation. Sine theta equals O over H. Substitute everything in. Sine 10 degrees equals our opposite, which is what we're trying to find out, which is our friction force, over our hypotenuse, which we worked out is 15680 newtons. That's our force of gravity. And so now to rearrange, I times this side by 15680 to cancel that out. That means I have to times the other side by 15680. Okay, so plugging that into the calculator, what we get is 2722.80 newtons, which is going to be equivalent to 2700 newtons, which has been rounded in the question. But if you've got the specific answer, you get this question correct. Okay, so as you can see, it's pretty useful to add in the angles before we go ahead, because it comes in handy for the trigonometry, which comes later on. Don't forget your units, be careful of rounding, and use my handy little trick of displacing that gravity vector to figure out where that angle goes, because it's a common mistake to pop that angle that they give you between any two vectors, and we don't want to do that. So a little exam tip for you if you come across a question like this. But other than that, well done. Let's see if we can move on to the next question.